Okay, so looks like you found the second group of verifications. Hopefully you worked on them before you're looking at this. So let's talk. Which side did you work on? The left? I agree with that. There's a lot going on the left. And I'm noticing I've got sine and cosine and tan and cotan floating around in there. And so I know what I'm going to do. What did you do? Good. You took tan and cotan and converted it to sine and cosine because I've got sine and cosine here. Most of the time, getting down to bare bone basics, like with sine and cosine, is the best way to get started when you've got a lot going on like this. So, I have sine squared theta. How do you write tangent? Sine over cosine, good. Remember to put the thetas in there. And in the denominator, I've got cosine squared theta. How do you write cotangent? Cosine over sine, good. Now technically, this has a denominator of 1, so I'm basically subtracting fractions, right? And to subtract fractions, you need to have a common denominator. So in the numerator, multiply top and bottom by cosine. And in the denominator, top and bottom by sine. So take it slow. I've got sine squared theta times cosine of theta minus sine of theta, right? Because I can write the numerator as one big fraction now. It's all over cosine theta. And in the denominator, so I've got cosine squared theta, and we're multiplying it by sine. So we have the same denominator, right? In the denominator, we have sine of theta, right? Okay. And now I multiply, now I've got a division of complex, I have a complex fraction here. Because there's a fraction in the numerator and a fraction in the denominator, and it's just not nice looking, is it? Okay, so what do we want to do? How about we make this a division problem, right? And when it is a division problem, wouldn't you multiply by the reciprocal of the denominator? And if you're like, I need to see that, okay, no problem. I'm just going to use a finer marker because I'm running out of board space. So cosine theta minus sine theta over, that's the numerator's fraction, right? And you're dividing by the denominator's fraction. Agreed? And then this would turn to multiplication and this fraction would reciprocate. Are you with me on that? Are you buying it? Good. And by the way, you probably have oodles of room to go down on your paper, which I highly recommend you do. I'm just running out of board space, so I have to write it this way. Okay. So now that I've reciprocated it, I was hoping something would cancel. Not seeing a whole lot canceling right now. But you know, this thing is cumbersome. And I'm noticing there's two terms, and both terms have a sign in it. Agreed? So what happens if I factor out of this numerator a sign? Like I said, sometimes this is trial and error. You just don't see all the crumpled up pieces of paper that I threw away. So I factor out sine from here. I am left with, I am left with, right? All over cosine theta. And over here in the denominator, if I factor out, do you notice they both have, like the first term has a cosine in it, and so does the second term? So if I factor out a cosine, then I've got cosine theta sine theta minus 1, don't I? Do you agree? Okay. Oh, wow, looky. Do you notice the parentheses? What's going to happen? Yeah, these parentheses are going to cancel, aren't they? So in the first fraction, I just have the sine of theta over the cosine of theta. And I'm multiplying the second fraction simply by the sine of theta times over the cosine of theta. Well, gee, that gives me sine squared theta over cosine squared theta. And isn't that just tangent squared theta? Which is what we have over here on the right side, tangent squared theta. They're like, I know, it's crazy how it works out sometimes. But it works out because you just take one step at a time. Remember, we converted tan and cotan into sine and cosine, so the left side had nothing but sine and cosine in it. And then we got a common denominator for the numerator and a common denominator for the denominator's fraction. We recognize this is a division problem because remember, that means division, so we rewrote it with the division sign, which makes life easier. And knowing we were dividing fractions, we multiplied by the reciprocal of fraction 2. And then we took a shot in the dark because this numerator and this denominator were not exactly the same. I couldn't cancel. So I took out what was in common and it left me with something I could cancel. And hello, tangent squared from there. Good? Okay, review this if you need to rewind it. In the meantime, example number 2 coming your way. Okay, so problem number 2. I'm going to be honest with you. This is one of those problems where I tried a couple of different ways and threw the paper away in the trash can. And so you don't necessarily see my trial and error before you see me working this problem out here. So let's get started. Let's take a look. Which side did I start with? Well, let me ask you, if you tried this problem, which I'm hoping you did, which side did you start with? Good. I agree to start on the left side because I have powers over there and I can at least do something with the powers. So let me look in the numerator. The numerator, I'm noticing, is the sum of perfect cubes. Well, I can factor that. And you're like, uh-oh. I know, you have to remember how to factor perfect cubes, don't you? Well, let's see what you get from here. So it's always 2 parentheses, even though it's cubes. So I have the sine of theta, whoops, and this one has the sine squared theta. I have cosine of theta, and at the end over here has cosine of theta. And in the middle, I'm going to need more room because I didn't make that big enough. In the middle is the multiplication of these. So it's sine theta, cosine theta. And like I said, there's a cosine squared theta here. And now my SIGN, my signs. Do I put addition in all of them? Do I put addition and subtraction? What do I do? Since this has addition, this has addition. And then it alternates. Okay. Over. Now, the denominator is not so obvious what to do. This is an interesting little trick, shall I say? And let me kind of sidetrack you a minute so you can understand the trick. You know, if you had 1 minus x, wouldn't that be 1 minus 2x? Well, I'm going to go backwards, and I'm going to separate out the subtraction problem. So I am going to write this as 1 minus cosine squared. Whoops. Yes, sorry. Minus another cosine squared. Because wouldn't that be a negative 2 cosine squared? Okay. And now you're like, well, now what do I do? Here is where you have to kind of do some trial and error and observe some things. I'm noticing in the denominator from Pythagorean's theorem, which we've done plenty of times, that this is nothing more than sine squared theta. So let me rewrite the numerator. I'm not doing anything to the numerator. Not a thing. I am just rewriting it. Actually, I'm going to do something. And it's in this parenthesis. Notice and see if you can do something in this parenthesis right here. What do you notice? Ah, good. Some of you caught it. And I am going to write it down. Sine squared plus cosine squared equals 1. Do you notice you have cosine squared a positive and sine squared? Isn't that just a 1? 1 minus sine of theta cosine of theta. So I could do something up there, couldn't I? Now let me get to the denominator. 1 minus cosine squared, right? If I subtract cosine squared on both sides, isn't this just sine squared? So wouldn't I have sine squared theta minus cosine squared theta? Like I said, this one was a lot of trial and error, but I'm trying to show you what my process was when I finally got to this point. Because this trick, we're used to going this direction. But you know, if you can go one direction, then you can go in the reverse also. And we have to remember to reverse things sometimes. And because of that, I end up with the difference of perfect squares, which gives me a factoring I can do in the denominator as well. And maybe some of you can see the step ahead that's going to take place. And if you can't, please don't worry about it. This might be one of those problems that you're like, I'm going to go back and slowly review this to make certain I catch everything that happened. That is a sum of perfect squares, right? So couldn't I write it as sine of theta plus cosine of theta times sine of theta minus cosine of theta? Do you see what's going to happen? Yeah, the sine plus cosine cancels out, don't they? And it will leave me just 1 minus sine of theta cosine of theta over sine theta minus cosine theta. And you're like, now what? Yeah, good question. On the right side, I've got secant and tangent. You don't have sines and cosines. All right. Here's another not so obvious something you can do. Tell me, secant, and I'm observing because I legitimately need to make this side, the left side, look like the right side. So since I'm kind of stuck at this point, I'm making observations. And I'm noticing that secant is 1 over cosine. I'm not moving anything. I'm not multiplying the right side by anything. I'm just observing. And I'm noticing tangent is sine over cosine. So both of these trig functions, if I write them back to the basics, are over cosine. Well, I'm noticing there's a 1 here, and if I could put a cosine under it, I'd get secant, right? And I'm noticing there's a sine here, and if I could put a cosine under it, I'd get tangent, wouldn't I? So here's what I tried. I decided to take this numerator and multiply by 1 over cosine of theta. And if I do it to the numerator, there you go, you have to do it to the denominator. Are you with me? Okay. So I'm going to continue this over here because I'm running out of board space right there. So I'm just look at the numerator. 1 over cosine times 1 is 1 over cosine theta minus, and then I'm going to take sine theta times cosine theta and multiply it by 1 over cosine theta, which gives me this lovely fraction. It's okay. It's going to work out. Now the denominator. I'm going to take sine of theta multiplied by 1 over cosine theta. Good. Minus, and now cosine of theta times 1 over cosine of theta. You're like, you can simplify that. You're right, I can't. I don't want to simplify anything yet, though. All I want to do is multiply the numerator and denominator by 1 over cosine theta so I can see what's happening here. And so now here's what I'm noticing. What's 1 over cosine? That's just secant. What happens on the second one? The cosines drop and it leaves me just sine. Okay, what's sine over cosine? Tangent. And cosine over cosine is 1. I think I made a mistake somewhere. Because I have a minus 1 and that should be a plus 1. I'm going to pause the video. Maybe I wrote this incorrectly. Maybe this should have been a minus 1. I'll be right back. Okay, I found my mistake. You know where the error was? Yeah, right here. This should have been a minus sign. You know, it helps if you copy things correctly. So that should have been tan of theta minus 1 in the denominator. Woof! Because, thank goodness, my left side now looks like my right side. Secant of theta minus sine of theta over tangent of theta minus 1. This was a very interesting verification. It was obvious to me anyway that since this was the sum of perfect cubes, I was going to factor the cubes and see where that took me. This was an interesting little backward step. Do we use it often? Not really, but we use it sometimes. So you kind of have to keep that in your repertoire. And it allowed me to get the difference of squares and allowed me to factor and allowed me to cancel. And this is where I kind of got stuck and I'm like, well, now what? So I observed that the right side, which is what I was trying to make this look like, secant and tangent both have denominators of cosine. So if I could get that one to have a denominator of cosine and that sine to have a denominator of cosine, I'd be much closer than I was here, which is why we multiplied the numerator by 1 over cosine, both terms, and the denominator by 1 over cosine, both terms. And gratefully from there, everything fell into place like I wanted it to, like I was hoping it would. Cool? Okay, this might be a problem for you to review again, but in the meantime, last problem, number 3, coming your way. Okay, third problem, how'd you do with it? Okay, let me ask you this. Which side did you work with? The left? I agree. We're going to work on the left side. So give me a starting point. What did you do? So you notice the denominator was the difference of perfect squares because they're both fourth powers, so it's a difference of perfect squares. So what'd you do? You factored? Okay, that's a good start actually to the denominator. I agree. So the numerator, do you notice it's this parenthesis squared? So as opposed to leaving the parentheses squared, I think I'm just going to write it twice to see what might transpire. I think I'd rather write it twice than leave it with a square there. So I can literally see all the pieces to my puzzle. With me? Okay, so the denominator is a perfect square, or difference of perfect squares. Tell me what you wrote. I heard you. I heard cosine squared theta minus sine squared theta. And then you multiplied it by cosine squared theta plus sine squared theta. Good. I'm agreeing. And it equals that. Got it. Now what? Isn't that a Pythagorean identity? doesn't this just equal 1? Because remember, cosine squared plus sine squared equals 1. So isn't this just a 1 down here? I agree, which means we have in the numerator 2 cosine squared theta minus 1 times itself over just cosine squared theta minus sine squared theta. Okay, got it. Remember, this parenthesis is just a 1. Got it. Oops, I forgot to write my thetas in. See, sometimes I get lazy and I forget. All right, now what? Okay, so I'm hearing a couple of different things. Me personally, here's what I'm recognizing. This denominator looks really familiar. It's not a Pythagorean trig identity because Pythagorean trig identity says cosine squared plus sine squared. This is cosine squared minus sine squared. So my brain is like, oh, wait a minute. You know what that is? It's a double angle. Cosine of 2 theta equals cosine squared theta minus sine squared theta. That's a double angle down there. So I can actually rewrite the denominator as the cosine of 2 theta. You're like, why would you do that? I mean, I want this. There's no double angle. Why would you do that? Hold on. Hang in there. There's a reason I'm noticing that because I remember that this double angle can be rewritten 3 different ways. Pythagorean's trig identity, right? Okay, let me write it down here. Pythagorean's trig identity looks like this. I can rewrite this as the cosine squared of theta equals 1 minus sine squared theta, can't I? I can also rewrite this. This is one way. I can also rewrite this by moving cosine over and saying sine squared of theta equals 1 minus cosine squared theta. I can get cosine squared by itself or I could get sine squared by itself. The reason I'm saying that is because if I make a substitution here and I say, let's see, cosine squared is 1 minus, sine squared is. So if I leave cosine squared by itself, sine squared can be rewritten as 1 minus cosine squared, can't it? Which gives me cosine squared theta minus 1 plus cosine squared theta, which will give me 2 cosine squared theta minus 1. That's also another way of writing cosine of 2 theta. Sorry, this pen decided it was having a little bit of a challenge. So the cosine of 2 theta is exactly what I have in each of those parentheses. So I'm going to rewrite each parenthesis as simply the cosine of 2 theta multiplied. And they drop out. Yay! So I have the cosine of 2 theta equals. And you're like, yeah, but I still need that. You're right, I do. But hold on. This double angle has one more variation. I can say the cosine of 2 theta. Here I plugged in for sine squared. Got it. What happens if I plugged in for cosine squared? Cosine squared is 1 minus sine squared theta, isn't it? And then minus this other sine squared theta. It's 1 minus 2 sine squared theta. And that's exactly what I have right there. So I can rewrite this double angle with this variation. These double angle identities are all written down for you. But I don't always remember them because I don't have them memorized. And if they're not available to me, I need a way to remember them. And this is how I remember them, just like Pythagorean's theorem. I've got cosine squared plus sine squared equals 1. I have that memorized all day long. But the other one that involves tan and secant, and the other one that involves cotan and cosecant, I don't necessarily have those memorized. But I can figure out how to derive them. Just like this, I can figure out how to derive the other two as long as I know how to rearrange Pythagorean trig identity. Anyway, this was an interesting step to turn it into the double angle, because then once it was there, they canceled, and you could rewrite it as a single angle. Hope this makes sense. Rewind, go watch whatever you need to watch to kind of refresh the brain a little bit. And I'll catch you guys on the flip side.